everyone. Now, since we are on the topic of manufacturing with glass-like carbon, let's also talk about making micro-scale structures using glass-like carbon. So, what are micro-scale structures? These are the structures that are in the micrometer size range. You know, we discussed this in detail that if you have very large structures made of polymers and then you convert them into carbon, what happens is these thick structures, they may end up having some bubbles trapped inside of them, trapped in the core of the material. These bubbles are caused by the byproducts, with the tar-like materials, the synthetic gases that are released during the pyrolysis of the polymer. And now, since the structure is too big, they are not able to anneal out in an efficient manner. And also, the carbonizing matrix is a very complex material, and its thermal conductivity may also differ. So once it becomes more carbon, you know, it has a higher fraction of carbon, then the thermal conductivity may increase, but what you have in the core may have a lower thermal conductivity because of higher impurities and also the trapped bubbles, and then it becomes, you know, then your overall structure, you cannot call it glassy carbon structure because some of it is not glassy carbon really, or it has different property. So what do? You try to optimize your size. So in the case of industrial glassy carbon devices or large scale glassy carbon structures, the optimum size is smaller than 5 millimeter. Okay. Now the point is, if we can go down from centimeter scale to millimeter scale, why not millimeter to micrometer or micro to nanometer? The idea is that the smaller the size, the better the quality of your carbon. Or not better quality, but in that case you require slightly lower heat treatment temperatures, because you now are able to provide more surface area for your byproducts as well as defects to anneal out. So why, by the way, defects also would like to anneal out? What are defects? In the case of elemental materials, so let's not talk about, you know, doping induced defects and so on. For an element, defects are, in the case of carbon, non-six-membered rings, so non-crystalline structures that have a certain strain. Okay, or these are the kind of structures which will also lead to distortions in your otherwise graphitic material. These structures are actually higher energy structures, and they will try to anneal out as long as, you know, it is possible. It is not possible if you have these strongly curved carbon structures, or if you have some of these strongly curved structures completely, they convert into fullerene-like structures. They become completely closed. So they are spherical now, or cage-like structures that we call. So once you have a defect or a bubble or a void trapped inside these curved carbons, then it will be very difficult for it to break that structure and you know, get out of the material. But there are also several voids which are not really, for them it is possible to anneal out. But what we need to do is we need to provide it certain energy in the form of heat. And also, you should remember that when these defects anneal out, let's say if a 7-membered ring tries to convert into a 6-membered ring, which is its most you know, energetically favorable state, in that case you will also have a more graphitic order, which means you will have more A-type organization, because now there is a possibility when you have all 6-membered rings, it is possible to have this kind of hexagonal graphite-like arrangement, crystalline arrangement, which was otherwise, once you have 5-membered rings, then you will only have this random rotation of the sheets on top of each other, what you would call graphenic sheets and not graphene sheets. I'm not calling them graphene because they contain defects. Okay, so these are the fundamental concepts. Also, in the case of microfabrication, you have the same principles are the same. So if you want to get glass-like carbon, what do you want? You need a polymer which undergoes coking, but it does not become so soft that you lose the shape. This is also again valid for the large-scale structures as well. So that is number one, and number two, you should have the right fabrication techniques. The fabrication techniques is what we are going to talk about. Your carbon content in the polymer should be high. So these are the things that are valid for everything. The only thing is that now we have we need, because we have very specialized microfabrication techniques. Now we are not using the traditional milling and drilling and turning techniques, because microfabrication has its own set of fabrication techniques. This is what we are going to talk about. So we need polymers that are compatible with those fabrication techniques and that are compatible with your carbonization. So both conditions should be satisfied. Also, one more additional factor is that when you're doing microfabrication, you're typically making structures onto a substrate. Substrate means, yeah, any flat structure. On top of that you will make your devices or structures or whatever. Because micrometer scale things can be very small. You can imagine that. So these, you will not make them individually. You will rather do a batch fabrication process, which in fact is the advantage of microfabrication. So the overall idea, the fundamental idea of microfabrication or reducing the size of the structures and devices is to, number one, be able to use less material and do batch fabrication. Number two, you have higher surface to volume ratio in all of these structures. So higher surface area always helps. How? Let's say if you take an example of a biological sensor. What does the sensor have to do? What do sensors do? They sense something. Biosensor would sense some biological molecule, which can be a disease, antibody or antigen or any bacteria or virus. This device has to sense it, to catch it, to chemically attach to it. If it has a larger surface area, then it will be able to catch your whatever is the desired molecule from, even when it has a very low concentration. Because now it is in contact of more liquid, because it has more surface area. Similarly, if you think of batteries, let's say lithium ion battery. So lithium ion requires more surface area to go inside the structure and come out charging and discharging. So these are also so increasing surface area, reducing the overall footprint of the device. Overall footprint means overall size. So if you want a chip that fits inside your mobile phone, then you don't want it to be too large. So the weight is reduced, the size is reduced, and the functionality, the sensitivity is increased. So this is the overall idea anyway of microfabrication, and that is why you want to have specialized fabrication techniques, specialized materials, and let's see if we convert them into carbon. Is there any advantage of that? We know the advantages of carbon. So now let's talk about what are the things that we do and how do we make these devices. So you want to remove the byproducts and defects. Yes, okay. Now, as I also mentioned, that you may get more graphitic order at lower pyrolysis or heat treatment temperatures if you have easier annealing of defects, and also some some polymers. We will talk about this. So there are some polymers which are used for many microfabrication techniques, especially photolithography. These are actually able to give you glass-like carbon. So this is what we will talk about. So before that, let me talk about some very fundamental things about microfabrication. So I'm assuming that you don't know anything about microfabrication at this point. So what is micro? Micro is 10 power minus 6 meter. That you know. So it's so here I have shown a scale where you can see. If you plot it on a logarithmic scale or plot, then you will have the same distance between 1 meter and 1 kilometer that you have between 1 micrometer and 1 nanometer. So it's the order of 3. So you can see in terms of powers of 10, how do these different landscape, the different dimensions look like. What we are talking about right now is the micrometer scale fabrication and not nanoscale fabrication. Also, another important thing is that we would typically call it microfabrication and not micro manufacturing. But in principle, we are making something. You can call it fabrication, you can call it manufacturing, or anything. The idea is that fabrication is just a term which sounds a little more sophisticated. Manufacturing sounds like you need good old fashioned big machines, lathe machines, and you require physical labor. So just to make it sound, softer in a way, you can use the term fabrication, which is more commonly used, but manufacturing, you're making something, you know that. Okay. So now, what device? So let's talk about device. What device would I call micro device? Anything which is smaller than anything which has its dimensions in 10 power minus 6 meter scale. Can I just call it micro scale device? Or is it number one? Number two, should I have all the parts of that device in the micrometer scale? then the overall device will itself be very small. Then when you see the chips that are on your inside your phone or something, not every part of it. So some part of it, which the circuitry and so on, that might be in millimeter scale. So does the entire device have to be in the micrometer scale? So well, there is this rather formal definition of microscale device is that when your functional element is smaller than 100 micrometer in size, then you call the device micro device. And same thing actually is also applicable to nano devices. There the functional element is smaller than 100 nanometer. What is a functional element? Every device has a function. So let's say if I have the sensor, the part of that device that is actually doing the sensing. The rest of it may be some cables or some, because you made contact pads because you need a readout from the device. So there will be, for the circuitry, you will do a lot of things. But the part that is actually performing the sensing, function, that is what should be smaller than 100 micrometer in the case of microscale devices. Now, microscale devices are also called microsystems because, we are talking about devices right now. We are talking about the entire system and not just one individual structure. So when you have this system which performs a microscale operation or function, your functional element is smaller than 100 micrometer, then you call it microsystem or you call it micro device. Okay, now they can be further divided, of course. They can be sensors, they can be, actuators, they can be batteries also, microscale battery electrodes. There can be many other, definitions, so classifications of these devices. One important class of microscale devices is what is known as MEMS devices. The full form of MEMS is micro electromechanical systems. So as the name itself suggests, you have something to do with electrical properties and something to do with mechanical properties. Now, these are electromechanical systems. So the definition of MEMS is that this is a class of micro devices where you either utilize mechanical properties of that material or of that structure to gain or to obtain an electrical signal or a readout. Or the other way around. Either you use the mechanical properties to get electrical signal, or you use the electrical properties to, let's say, mechanically vibrate your structure. So these type of devices are known as MEMS devices. But not all microscale devices are MEMS. That you need to remember. So there's some examples of MEMS you can actually do in an internet search and find out a lot of examples of MEMS. But remember that there are not all microscale devices are MEMS. That is very important because there are, other than MEMS, there are other types of microscale devices. For example, a battery electrode that has an electrochemical property, an electrochemical function. You don't call it MEMS device because that is passive. That does not, there is no mechanical movement of that structure. Also, you're not getting an electrical signal because of the mechanical movement and so on. So there is. They are not, but they are, if their dimensions are in microscale and if the functional element is smaller than 100 micrometer, you will still call them microscale structures or devices. So there are also other examples like biosensors. If I have a microscale, structure and I immobilize some enzymes on top of it, and those enzymes are then performing certain function and they are sensitive to certain biological molecule, this entire setup may not be a MEMS device, but it is a microscale device. So basically, the idea is that all MEMS are micro devices, but not all micro devices are MEMS. Okay, so now let's talk about the microfabrication technique. So now you understand the fundamental, what is the definition of microscale device and so on. Okay. What are the microfabrication techniques? Well, as I said, that you may not always use the traditional manufacturing tools, but sometimes you may also, some of the manufacturing tools can also be used. But before that, let's talk about what is a device anyway. So the device should have a function. Device should have a functional element. But sometimes when you say microscale structure, remember that the structure may not be a device. So there is a difference. What is a material? material is something like carbon. So you see in this image, material is a material. We generally use the term material for anything that is bulk, that is tangible, that has some form. So that is a material. Carbon in a very general way, we can call carbon a material. We can call graphite a material. We can glass like carbon a material. We can also call carbon nanotubes a material, but since it has a certain well-defined structure at the nanoscale, then we call it a nanomaterial. Okay, so material, nanomaterial, these are still, we have not utilized them in any specific fashion. However, now if you take this carbon powder or carbon nanotube powder, and then let's say you mix it into a resin and you print it on top of a substrate. And that's why I said the substrate becomes important in the case of microscale. So you made lines out of it, which look like some interdigitated electrodes, these are called. So these are not yet electrodes in a way, but you want to make microelectrode arrays. So even if you make, so whatever design you had in mind, once you make it on top of a substrate, then you call it a structure, micro scale structure. And then you also make the contact pads, you also make everything else, whatever, how will you get the readout from your material? You may actually integrate certain CMOS chips. You can use, when you are completely fabricating a system which can perform a certain function, then you call it a device. So this is the difference between structures and devices. Okay, that is something you already know, but just to keep in mind. Okay, now similar to large scale manufacturing, you can also perform your microfabrication using top down or bottom up manufacturing approaches. So top down is when you take a bigger piece of something and then you remove the unnecessary parts. So you also can call it a subtractive technique. Or you can use bottom up, which is called the additive technique. Techniques like 3D printing, layer by layer arrangement of something, or certain biological processes where smaller molecules or cells will make a larger organ together. That's also a bottom up process. A lot of natural biological processes are rather, in fact, bottom up processes. So you can use both of these techniques depending upon the material that is available to you, and depending upon also the ease of fabrication and the overall cost, and keeping all of these things in mind. Also, whether you want to use batch fabrication or you want to use individual fabrication, serial manufacturing techniques. So based on all of these things, but you have both types of techniques, bottom up and top down, also in the case of microfabrication. Okay. Now, some of the traditional manufacturing techniques are actually also usable for micrometer scale structure fabrication. So, actually, you will be surprised to know that there are drill bits that are, you can find drill bits which can actually precisely give you 50 micrometer diameter holes. So it's not impossible. There are certain techniques which have been translated into the micrometer scale. Some other examples I have mentioned here, for example, EDM and ECM, electric discharge machining, electrochemical machining, wire EDM especially. These are the techniques that are also used for making micro scale structures. In fact, sometimes also in the past, people did make micro scale structures, but they did not, those were not the functional elements in most cases. That's why the technology was not so widely utilized. But micro scale fabrication has also a lot of gold jewelry. You will, if you go to a good old-fashioned gold jewelry manufacturer in Jaipur or something like that, you will realize that actually they are using a lot of techniques which are giving you micro-scale structures. But they are not devices. You're making jewelry out of it. You're not really making electronic devices. You're not. So fabrication techniques were available, but now we are using them more for the devices, and also now there is a market for these devices. Now you have larger equipment that require micro scale devices. So it is this nowadays. That's why microfabrication has become popular in a different way. But as I mentioned, some of the traditional techniques can also be used for making micro scale structures. Okay, but then there are also certain new techniques which have been developed specifically for microfabrication applications. So they may not be used at larger scale. For example, various lithographic techniques. Now, the term lithography actually means, litho means a stone and graphy means carving something. Graphy is a term which graphy and even graphite is related to that. This term is actually used for drawing things. Graphy is to draw something. Okay, and since graphite was used for drawing things, that's why it is called graphite. Okay, so these all words are related. But lithography as such is a technique which is used for, this term was used for carving structures onto the stones. And now we carve structures on top of silicon wafers, so we call that also lithography. And how do we carve structures on top of silicon wafers? We don't sit and scratch the silicon wafer. What we do is we make a polymer film on top of your silicon wafer, or any other substrate for that matter, but silicon wafer is the most commonly used substrate. So you make a film of polymer and then you remove the undesired parts and keep the desired parts. So it is as simple as that. That would be called your lithography. But now the question is, how do you remove the undesired parts? And how do you determine what structure do you want to make? And how do you actually make that structure? So this is where the lithographic techniques, that is where we need to learn about the various lithographics. So actually, there is not just one lithography, there are various lithographic techniques that will depend also on the polymer, on the size of the structure. So, for example, photolithography, as the name suggests, it has something to do with photons, something to do with light. So, this is a technique where you utilize the UV light as your tool. That is what is used for removing the undesired parts of the material. Similarly, there is something called electron beam lithography. So you have a beam of electrons that is used for carving the structures out into your polymer. There is X-ray lithography where you would use X-rays. There is something called nano imprint lithography where you will actually use a mechanical push to pattern your polymer. So all of these techniques are used now in the case of microfabrication.